Let's imagine that a certain population has a mean age of 25 years. The standard deviation of the population is 5.6, and the ages in the population are positively skewed. That means that in the population, most people are down at the younger end, and there's fewer and fewer older people in the population. There's fewer and fewer people out in this direction. Let's also imagine that a certain person wants to know the mean age of this population. In order for the person to calculate the mean age of this population, the person would have to record the ages of all people in the population, and then calculate the mean of the data. The person doesn't have enough time to do that, so the person takes a random sample of 43 people from the population, records their 43 ages, and then calculates the mean of the 43 ages to estimate or get a rough idea of what the population mean equals. Whenever a sample is randomly selected from a population and a sample statistic is calculated, there's a sampling distribution involved. The sampling distribution includes all of the possible combinations that could become the random sample. When a person takes a random sample from a population, the person is pulling one sample from the sampling distribution. The sample could come from anywhere inside of the sampling distribution. If the sample comes from the left end of the sampling distribution, the sample statistic will be a low number. If the sample comes from the right end of the sampling distribution, the sample statistic will be a high number. And if the sample comes from the middle of the sampling distribution, the sample statistic won't be unusually low or unusually high. It'll represent the population pretty well. Let's talk about the shape of this sampling distribution. In this situation, the shape of the sampling distribution is predictable. When a sample is randomly selected from a population, and a sample mean is calculated, the shape of the sampling distribution is determined by a rule called the central limit theorem. The central limit theorem says that a sampling distribution of sample means will be normal if the population is normal, and will be roughly normal if the sample size is 30 or larger. In this situation, the population that's being sampled isn't normal, but the sample size is above 30. That means that this sampling distribution is roughly normal. Since the shape is roughly normal, the population mean is at the center of the sampling distribution. Also, outcomes further from the population mean are less likely in both directions. The sample mean is likely to come out to a number in the middle area around the population mean. It's not likely to come out to an extreme number way down here, or an extreme number way up here. Even though the sample mean is likely to come out to a number around the population mean, it's not likely to come out exactly to the population mean. Whenever a sample is randomly selected from a population, and a sample statistic is calculated, the sample statistic is almost always a little bit different than the population parameter, or population statistic. The sample statistic is almost always a little bit off target. In this situation, it's actually not possible for us to know exactly how far the sample mean will fall from the population mean. The sample mean could fall anywhere along this number line. However, it is possible for us to make a rough estimate of how far the sample mean will fall from the population mean. We can do that by calculating a value called the standard error. To get the standard error, we need to divide the population standard deviation by the square root of the sample size. The population that's being sampled has a standard deviation of 5.6, and the sample size is 43. That means that we need to divide 5.6 by the square root of 43. When we do that, we get a standard error of 0.85. This number is telling us that the sample mean is likely to fall about 0.85 from the population mean. The standard error provides us with useful information. The only problem with the standard error is that it doesn't tell us exactly how far the sample mean will fall from the population mean. The sample mean could fall anywhere along this number line. However, we know that the sample mean is likely to fall somewhere in this middle area around the population mean. Imagine that the sampling distribution has three areas: the lowest 2.5% of possible samples, the middle 95% of possible samples, and the upper 2.5% of possible samples. The sample mean has a 95% chance for a 0.95 probability of falling somewhere in the middle 95% of the sampling distribution between these two boundaries. What if we wanted to measure the width of this area in which the sample mean has a 95% chance of falling? We can do that as long as the sampling distribution is normal, like it is in this situation. We just need to know the z-score of this boundary and the z-score of this boundary. In a normal distribution, 95% of the values fall between negative 1.96 and positive 1.96. What we're going to do is take this z-score of 1.96 and use it to calculate the distance from the population mean to this boundary and the distance from the population mean to this boundary. Those two distances will be called the 95% margin of error. How can we do that? Well, we just need to remember that in a sampling distribution, a z-score is just the number of standard errors. This z-score is telling us that this point is 1.96 standard errors below the population mean, and this z-score is telling us that this point is 1.96 standard errors above the population mean. That means that to get the 95% margin of error that we're looking for, all we have to do is multiply 1.96 by our standard error of 0.85. When we multiply 1.96 by 0.85, we get the 95% margin of error. The 95% margin of error equals 1.67. So the distance from the population mean to this boundary is 1.67, and the distance from the population mean to this boundary is also 1.67. This result is telling us that the sample mean has a 0.95 probability of falling within 1.67 of the population mean. In other words, the sample mean has a 0.95 probability of falling somewhere between 1.67 below the population mean and 1.67 above the population mean. Let's actually calculate the number that's at this boundary and the number that's at this boundary. We can do that by taking the population mean and subtracting the 95% margin of error, and taking the population mean and adding the 95% margin of error. When we subtract and add, we get these two numbers. So the sample mean has a 0.95 probability of falling somewhere between 23.33 and 26.67. Now that we understand the 95% margin of error, let's take a look at what affects the 95% margin of error. One thing that affects it is the population standard deviation. When the population standard deviation gets smaller, the margin of error also gets smaller. Let's drop the population standard deviation down to 2.2 and see what happens. When the population standard deviation goes down to 2.2, the standard error drops. The standard error goes down to 0.34. Since the standard error dropped, the margin of error also drops. That's because we're multiplying 1.96 by a smaller number. This time, the 95% margin of error came out to 0.67. That means that in this situation, the sample mean has a 0.95 probability of falling somewhere within 0.67 of the population mean. So what happened is the population standard deviation went down. Since the population standard deviation went down, the standard error went down. And since the standard error went down, the margin of error went down. One other thing that affects the margin of error is the sample size. When the sample size goes up, the margin of error gets smaller. Let's raise the sample size to 70 to see what happens. Since we're randomly selecting a sample of 70 people, the standard error is smaller. The standard error went down to 0.26. Since the standard error went down, the margin of error went down. That's because we're multiplying 1.96 by a smaller number. The 95% margin of error is now 0.51. That means that, in this situation, the sample mean has a 95% chance of falling within 0.51 of the population mean. Now, let's look at a different situation. In the last situation, we were looking at a person calculating a sample mean to estimate a population mean. In this situation, we're talking about a person who's calculating a sample proportion to estimate the population proportion. We're imagining that a certain population is 57% male, and that a person wants to know what percent of this population is male. The person takes a random sample of 43 people from the population, records their genders, and then calculates the proportion of the sample that's male to estimate the proportion of the population that's male. Since we're taking a random sample and calculating a sample statistic, there's a sampling distribution involved. Once again, the sampling distribution includes all of the possible combinations that could become the random sample. The random sample is going to be one of the possible samples in the sampling distribution. In this sampling distribution, each possible sample, or each possible combination, has its own proportion of males. Right here, we might have a possible sample that's 47% male. Right here, we might have a possible sample that's 60% male. Way up here, we might have a possible sample that's 90% male. And way down here, we might have a possible sample that's only 10% male. Let's talk about the shape of this sampling distribution. When a sample proportion is being calculated, the shape of the sampling distribution doesn't depend on the central limit theorem. There's a different rule that's used to predict the shape of the sampling distribution. When a sample proportion is being calculated, the sampling distribution is roughly normal if n times p and n times 1 minus p are both at least 10. Let's see if this is actually true in our situation. We need to multiply 10 by our population proportion of 0.47. That's n times p. So this didn't come out high enough. Let me try it one more time just in case. We have to multiply our sample size, 43, by our population proportion, p, which is 0.47. So it is, n times p is at least 10, it's 20. So this checked off. Now we need to multiply n by 1 minus p and see if that's at least 10. So we multiply our sample size of 43 by 1 minus p, which is going to be 0.53. That's at least 10 also. So since both of these came out to 10 or higher, and they both checked off, this sampling distribution is roughly normal. Since the shape is roughly normal, the population proportion is at the center.